and let's go ahead and get started. So I am Harpreet Sahota, hacker in residence at Voxel 51. I've been here for just about 2 years. My background has kind of been math, coding, and things like that for a very long time. 15 years at this point, I'd say. Started off with, did undergraduate, graduate studies in math and statistics, worked as an actuary, biostatistician, data scientist, started going into deep learning maybe about 5 or so years ago. Worked at various startups since then, and have been quite happy at Voxel 51 over the last 2 years. Follow me on GitHub. I'm always, hacking away on stuff, and if you're curious as to what's new and hot in 51, then following me on GitHub is going to be the best way to get get updated on that. Dropping this stuff kind of at the top of the hour. If you feel that what I'm talking about is interesting and you enjoy it, you can follow along with me more on these channels as well. So X, trying to up my presence on X. So if you have X, please give me a follow. LinkedIn, GitHub as well. So now I'm going to tell you about what we're going to cover today. So we're going to work with this data set that came out in January of 2026. It's called the Action 100M dataset. This is published by FAIR, Facebook Fundamental AI Research. And we're going to start off by just talking about the data set. We'll go into a little bit about how the data set came to be, what the annotations represent, how the annotations came to be, the structure of those annotations. Then real quick, I'll point out that we're not actually going to work with an entire 100M data set. We have a subset that we're working with, and I'll describe that subset. And then finally, we'll get into some coding. We'll get hands-on with the data set and 51, and we'll kind of explore the two and see how we can use 51 and open models to explore and understand what is in this data set. So what is Action 100M? So this is a massive data set that came out of Meta. The full data set itself has like 147 million annotated segments across 1.2 million instructional videos. Instructional videos, for example, from cooking, do-it-yourself type of stuff, crafts, home repair, things like that. An interesting thing about this data set is that everything's kind of automatically annotated, so no human labelers. And the scale, of course, is impressive of this data set. It's absolutely massive, but the structure, I think, is really what I found to be most interesting. So every segment in this video has 5 different text annotations that are designed for different downstream tasks, and they follow a kind of hierarchical pattern. So a single moment in this video could have multiple levels of annotations, each capturing kind of a different level of granularity. And I think that's unusual in a data set. First time I've ever seen anything like this in a video data set. But also to create some kind of interesting challenges for how one would work with and kind of understand this data set. So I want to give a quick overview of how these annotations were made. So there was a 3-step process that went into kind of annotating this data set. So first they started off with this model called VJEPA2, and this extracted visual embeddings, and they used some type of hierarchical clustering to break down the video into a tree of segments, so root node and different leaf nodes. And each one of these nodes in this tree is like a different temporal scale. And then after they did this, they used 2 vision language models that captioned every node in that tree. So they used one of their llama models for kind of spatial detail on the most shortest segments. And then they have this model called Perception LM, and they did this more for kind of temporal kind of, capturing temporal dynamics for like longer clips. And then finally, they used GPT OSS 120B, ingested all those captions, cross-referenced them against each other and the video metadata, and then extracted kind of a clean, structured annotation through various rounds of self-refinement. But the key point for us is that second step. The captions, of course, could be hallucinated in a sense because they're raw. But then the stage three, it's purported to be really kind of cleaned and filtered out. And as you'll see later, once we get this data into 51 format and kind of use the local app to explore it, that we're only going to really concern ourselves with those GPT refined fields, since if you were to use this data set for anything, those are the fields that you would actually want to use. So as I mentioned, we're going to be working with the GPT fields. There are 5 fields. Every segment gets these 5 fields. They look redundant at first, but they're actually not. So each one is describing the same visual moment, but through kind of a different lens for different downstream tasks. So if you're training like a classifier, for example, like an action classifier, you might want to get like the brief action or the compact verb phrase fields. If you're maybe using this to pre-train some type of a robot, for example, vision language action model or something like that, then you'd want kind of detailed action and step-by-step instructions. If you want to build a search engine over these videos, then you really want detailed summaries with as much context as possible. Then finally, this actor field, it tells you who's doing what, and this matters, of course, in kind of multi-person scenarios. When I parse this into 51, as you'll see in a little bit here, each of these is what's called in 51 parlance a temporal detection field. And you'll see once we get to the app, and as I'm showing here in this short GIF, that you could toggle each one of these fields independently and kind of compare what each one tells you about the same clip. So you might be wondering, okay, like I've got one video, I'm clicking on one field, I've got all these different annotations for that one field. Like what do they represent? And so this was a part that kind of like tripped me up when I was exploring the data set. So I figured it's worth taking time to explore it in more detail. So each of these 5 GPT fields, it's not like a single label per video. It's a collection of many temporal detections, one for every node in the tree that has a span of more than 4 seconds. So what ends up happening is you might have a single video with like 50 or 100 detections in, like, for example, GPT action brief in that field alone. And some of them might overlap temporally because, they're at different hierarchy levels. But like the level 0 node or the root node will give like a brief action of maybe, for example, make almond butter that spans the entire video. Level 2 might be kind of more the fine-grained and granular actions, maybe spread almonds on the tray, and that spans maybe 5 seconds. And both of these will end up living in the same GPT action brief field, but like as a separate kind of temporal detection. As I was working through parsing the data set, of course, this it felt wrong to me. Like it just felt like, is this a bug? Is this an error? But it's actually not. It's by design. So just kind of to drill the point home and illustrate what they're showing here in this paper, this figure from the paper, we have like a parent node, and that's going to fully span the video, and that parent node contains its children nodes kind of by definition, right? So we see here this really concrete example, right? Suppose that maybe the 10-second mark of a video about how to make almond butter, you might have something like make almond butter that's active at level 0, and then blend olives at level 1, arrange olives on a tray at level 2, and then pour almonds onto the tray at level 3, right? So this kind of hierarchy of actions. So all these, again, live in the same field, cover the same moments, and they're all correct, but just at different kind of granularities. But the key thing is that within any like level, there's no overlap. And these sibling child nodes, they cleanly divide that parent's entire span. So that's a really interesting way to annotate a data set. Just to illustrate this further, just showing kind of one sample here, we have a root node that's going to span the entire video. Then we have children nodes, for example, at level 1. Those siblings are going to sit side by side. When one node or one detection ends, the other begins. So there's no overlap between the children. But together, they perfectly cover the parent span. And then each of these gets split again at level 2. And so you might have 4 segments tiling the whole video end to end. But there's still no overlap at any particular level, like within any particular level. The overlap would happen across the different levels. So like, for example, at the timestamp, 30-second timestamp, for example, we might have level 0, 1, and 2 all having an active annotation. And those 3 labels will simultaneously kind of annotate a different level, a different granularity within that video. And then each one of these detections will have the level, we'll see this in a little bit more detail when we open the app. We'll have the level, the node ID, the parent ID, and all of these are like attributes so that you can filter to one level or reconstruct like the full tree if you needed parent-child relationships. So for example, if you just filter on any particular level in FiftyOne, you'll get a clean kind of non-overlapping timeline of these various kind of, we'll call them mid-tier or mid-granularity action steps. A good analogy, I think, is just like Russian dolls kind of laid out on a timeline. You have a larger doll that contains 2 medium dolls, and each of those contains 2 small dolls. And then, the medium dolls don't overlap with each other. The small dolls don't overlap with each other, but a small doll is always sitting inside a medium doll, which is always inside a big doll. So it's like kind of an analogy like that. I think that is potentially helpful. So we kind of got an idea of the data set, what it contains, the annotations, what they represent. So just kind of speaking more towards qualitative aspects of the data set. So from the paper, they give some interesting detail about what qualitatively what the data set is comprised of. And this is important to look through because before you build anything on top of the data set, you should understand what's actually in it. So first thing to do is maybe count the labels, right? And you see here immediately that within whatever model they use to determine this information, that speak to the camera like towers above everything else. Not surprising given that they're primarily focused on instructional videos. In an instructional video like this one, for example, I'm talking to the camera. It happens a lot. But this does dominate your training data, right? If you don't address this, right? So just something to keep in mind. The authors also mentioned that nearly 2/3 of the segments are under 3 seconds, and that's because the tree produces a lot more leaves than branches. And there's also some gaps. So anything under a 4-second clip has no GPT annotations. And about 3% of what remains is kind of like non-action content, like an intro, B-roll, or like an ad, or something like that. And so just kind of think about what granularity level is right for you and what kind of actions that you want to be able to capture. And they have this word cloud here. And from this word cloud, it's clear to see that the domain is entirely educational, a lot of cooking and do-it-yourself. Videos are heavily represented. Things like sports or social interactions just don't make much of an appearance at all. On the positive side, there's a lot of other interesting metadata to explore beyond these action labels. So they've got transcripts that are aligned to the timestamps, video titles, view counts, upload dates, like counts, things like that. And we'll see all this in a few minutes here. And within FiftyOne, we'll make them all kind of like filterable and gives us a way to understand and kind of subset the data set. As I mentioned, of course, we're not going to work with the full data set. The subset I have is just about 1,100 videos. Resolution is capped at 480p, and I only have 40 seconds of video because, well, disk space is an issue, right? So trying to keep it manageable, but yet still educational enough for us for the purposes of this workshop. And even then, even with what we have as a subset, it's still about 29 hours of video, still a lot of video, if you were to sit there and watch through it. So it's helpful for us to make use of some modern tools to help us get a better sense of, precisely what is in our data set. And this is how we're going to do that. So we're going to load the data set into 51 format. We're going to compute embeddings using Qwen3-VL embeddings. We'll also do some zero-shot classification using that same model. And I'll show you a couple of ways to compute embeddings with some different models. Then we'll use Qwen3-VL and then also Molmo2 to add some additional fields to our data set. And then we're going to use these newly computed fields to further explore the data set and maybe kind of think towards how it's possible to potentially do some kind of analysis and evaluation. So before I jump into that, there's some questions here. Is this create imbalance if we train directly, and what architecture can we prefer for training with this architecture? I don't fully understand your question. If you want to flesh it out a little bit further and drop it in the Q&A widget, that'd be much appreciated. But yeah, I'm not sure I fully understand your question. Now what we're going to do is jump right into some code. So let's jump right into some code real quick. This is all running locally. Pip install 51 is all you got to do. Pip install 51, and then you get the 51 package installed, and you can run this app locally. So this is the part where I'm going to go through the notebook at a high level. I'm not going to read too much from what I have here, because you could just read this on your own time after the webinar. I've put as much detail as I can to kind of keep it educational and instructional as possible for you. But we're going to try to understand what's in this data set. So, we have an overview of the data set. We kind of understand what the authors purport this data set contains, but we're going to look at it for ourselves. And we'll use kind of three different lenses to look at it. We'll look at, what does the raw data actually look like? And then we'll use some tools like open model tools, of course, Qwen3-VL embedding, Molmo2, and then Gina text embeddings 5 via sentence transformers. Then we'll get a second opinion, as this will all be laid out in the coming minutes here. But we'll use Qwen3-VL and actually Molmo as well. We'll measure the agreement between the different levels of these annotations, and try to figure out if we can find some hard cases, right? Where do the annotations we try to reproduce differ from what the ground truth is? And so we'll see all this in action using 51. So the question here is, when analyzing a film, is it sufficient to analyze only the visual frames, or must the accompanying audio also be examined, especially if the goal is to understand emotion or mood scene? Well, I'll give you the cop-out answer of it depends. It depends on what your use case is. In the case of this data set, all of the videos actually have audio, and we have the transcript from that audio as well. And what's interesting is, I don't want to get too ahead of myself here, but when I was using, for example, Qwen3-VL to do some type of annotation, it was picking up on information that could only really be pulled out from the audio. And actually, I don't know if Qwen3-VL under the hood pulls out the audio. I don't recall from the paper, but it seems to pick up on audio information. So I mean, yeah, audio might be useful if you're doing some type of downstream work case where you want a model to be able to do this task of, for example, speaker dietization, where it's like, okay, if someone's talking, like, where is that person relative to the camera in the environment, or who is it that they're talking to? I mean, that could be important for that specific task, right? Understanding emotion or mood of a scene, yeah, potentially audio can be useful. That definitely could be useful. But yeah, just depends on the use case. All right, so real quick, I'm gonna pull up the actual repo for us here. So 51 Video Workshop. the repo is here. And again, I'll drop a link here just to walk you through the setup, right? So you can open this notebook in Google Colab just by clicking that, and this entire notebook will be available for you in Google Colab. Of course, if you choose to run the models, you'll need significant compute. Slides are available here, and give you steps for what you need to do to set up your environment. So I have all the requirements necessary to make this work successfully here. I've pinned versions of transformers, torch, and torch vision. The models that we're working with are not yet fully compatible with the Transformers 5.0, so we stick to 4.57.1. These are left here in case you want to use flash attention. You could face issues trying to compile flash attention too with Torch 2.10. So just putting that out there, but you should be able to successfully recreate your environment here. Oh, did not mean to exit that. If you're running this on Google Colab, it is important that you uninstall Torch codec, because that'll just slow things down. So just a note here. But everything you need to do to get started is on this README. There's two paths you could take. You could download the data from Hugging Face from the voxel51.org. This will be the data set without any of the quote unquote enrichments that we do throughout the course of this webinar. But if compute is an issue, which it can be, like computing the stuff using Qwen3-VL and Molmo2, you need heavy compute and it's time consuming. For example, I use an H100, and when I was running Qwen3-VL to do its various things, that took hours. Molmo2 took about twice as long as Qwen. So for that purpose, I have a enriched data set here with all the embeddings, model outputs, and stuff that's here. And so a little bit of detail about what's in that. So, if you want to start from scratch, you can use this. If you want to work with the data set kind of with generations on it already, you can use this. In the event that you get rate limited by Hugging Face, just go to download scripts and it'll show you how to download the data set kind of manually. So that's what this does here. And it's configurable. I mean, you could adjust the resolution, the duration, and whatnot. So I'll leave that up to you. And then once you've downloaded these data sets, there's a script here to parse the data set into 51 format. So you can kind of work with the data set as we have here. So everything you need to get started is right here on this README with instructions on how to get set up and everything. We'll be making use of plugins. So 51 has a docs plugin. 51 has a plugin ecosystem, which means that it is extensible and hackable, and you can customize it to your needs and workflows. So everything's kind of community driven, and it's a great way to kind of get started with open source. And if you are interested in kind of building plugins and learning how to do that, but don't know the 51 ecosystem that well, we have a workshop coming up in a couple of weeks where my colleague Ad and I will show you how to vibe code a plugin so you can customize 51. But we'll be making use of a few plugins, this text evaluation metrics plugin, a plugin to help make the viewing experience for the captions a little bit more pleasant, and then just this pet project I have that you'll see as well. And then all the references and stuff are here. Cool. All right, so I make the assumption that you probably will likely want to start with a enriched version of the data set. Curious, before I jump into this, who's familiar with 51? If you are familiar with 51, drop a 51 in the chat. If you are not familiar with 51, drop a 50 in the chat. In the meantime, I'm going to go to LinkedIn and see if there are any questions, but let me know your level of familiarity with 51. All right, so I don't see questions on LinkedIn, so no worries there. So here, okay, cool, wow, all right. Overwhelming amount of people here are not familiar with 51. So what that means is I'll spend a little bit of time just giving you a high-level overview of what 51 is. So like I mentioned, open source, pip install 51, open source library. So the core concept in 51 is this dataset object. And dataset is just, kind of like I mentioned, the core object in 51. And this is a logical representation of your visual dataset. Not only of the visual assets in your dataset, but all the accompanying metadata, labels, predictions, and other fields as well. So this is all stored lightweight, MongoDB. You don't need to know anything about MongoDB to get started. You could just pip install 51 and you're off to the races. You don't need to know much about MongoDB, but all of the samples, their metadata, all that stuff is backed into a MongoDB dataset. There's a question here. Is datasets in 51 similar to data frame in pandas? A little bit not. And this is why I dropped a link here to kind of, for those of you who are familiar with working with pandas, trying to compare and contrast 51 to pandas, I've dropped a link here that you can check that out. So many ways to get your data into 51. So if we go to docs here, and in this notebook, I link you to the docs throughout, but let's just go to our docs and then using datasets. So I'll drop a link here as well. It's linked throughout the chat too. And there's many ways that you can actually, work with your data and get into 51 format. If it's in a common format, for example, if any of these formats look familiar to you and this is what you work with, then you can follow along here and use kind of like the built-in importer to import your data and get into 51 format. If your data set is like, what we have here, something that's not in a standard format, then parsing into 51 is quite straightforward. It's just a matter of iterating over your annotations and the actual media file, and then building out a sample, compiling the samples. Like all of this code you see here, this is just like standard Python, traversing a directory, walking a directory, getting information, getting file paths, getting stuff from the JSON-L, and then compiling all of it into 51 samples. So this is like really the only 51 thing that we're doing here. So build a sample and compile a list of samples and inject into the data set. Like I mentioned, the data set is the high level kind of abstraction 51, but then a data set itself is made of samples. So samples are like the atomic element of a 51 data set. So one kind of item in your data set is going to be called a sample. And the sample themselves are comprised of fields, right? So scrolling back up a little bit here, when we call the data set, we see sample fields. So these are all fields that exist on the data set. And each one of these are, 51 type. And if we were to peek in to a sample and see what it is comprised of, it looks something like this. We have a file path pointing where that file path is on disk, metadata, the information, various metadata, and then the actual detections themselves. So that's kind of like the hierarchy in 51. You have the data set. Data sets are comprised of samples. Samples contain fields, which are the metadata about the data you're working with. That metadata could be strictly metadata, or it could be label types and detections and bounding boxes or segmentation masks or classifications and things like that. So high-level crash course into 51. Now I mentioned everything runs locally. So once you do pip install 51, you run that code above, and then you load your data set. You can launch the 51 app. And so the 51 app looks something like this. Let me just move that down. So 51 app, and you can see here it's running locally. It looks something like this. So you can see it's just a way for us to inspect all of our media, but then also have alongside the media the different fields in our data set, as well as the different metadata as well, right? So for example, if we're to open up one video here, we can, for example, if we're interested in maybe GPT action brief, we can hit play, and then we could see that these are the annotations that come from Action 100M. So as we're looking at the video, we could see that these are all the action fields that are happening at that level of granularity, right? And we can filter here as well. So for example, we might just want a root node, and remember that root node is like the action that describes like the entire video, or we could just have like the mid-level nodes. And so the mid-level nodes are what is happening in each granular segment, which of course can have different levels of granularity as well. And of course, I knew that would happen if I try to get too crazy with the app. Oh, what did I do? All right, let me I need to open up the app again. Apologies for this. All right, where is my terminal at? There it goes. All right. And preview and editor, there we go. All right. So high level overview of the 51 app. So now what we could do is, of course, explore our data set a little bit more interactively. So we can create a dashboard. So we just hit the plus next to there. We can create a dashboard, and maybe we want to create a numeric histogram. And our data source, for example, could be the view count. We can call this view counts. The x-axis could be views, and we could change the bins. We can create that plot. We create this dashboard that we can interact with. So let's do it. I'm just going to create a few plots here that allow us to interact with the data set. Let's do bin size arbitrary, whatever you could choose whatever you like. Continue to add items here. Let's do another numeric histogram and the data set, the field that we want. Okay, so we've got view count, light count. What else could we look at? Maybe we'll do tree depth. So tree depth, remember, is like the number of nodes that are in that actual data set. So tree depth. All right, and then let's just make this. No, we'll keep it at 10. All right. So we've got this dashboard here that we can create. Right, and we can of course. All right, so note that I'm using this within my IDE, so it's not like the full interactivity that you would get if it was in the browser, but it's good enough. We could open this up alongside our app here, and then we could zoom in, for example, on here, and maybe filter here. So now we've got view counts between that range of 1,000 and something up to some other range. And it'll filter the data set here so that we see only those samples that have that particular number of views. And yeah, it's all kind of interactive and usually quite snappy, but of course I'm first time running this in like an IDE rather than just on my browser, but you can see that it's filterable and interactable. So yeah, that's how you can create dashboards real quick to kind of do some high level summaries of your data sets, interactive, point and click, everything filters down. All right. So question here in the chat, does 51 automatically support all new data sets on Hugging Face, or do you manually add support for each of them? Depends on the structure of the data set. If so, just pulling up our docs here. Our docs, and we go to integrations and look for Hugging Face. It's here somewhere. Right. Let's do loading datasets from the hub. If your dataset's like in a common format, like COCO or image classification directory tree, then it's quite straightforward to load that dataset as long as it's in this kind of common format. But otherwise, you would, if it's not, like more and more data sets are now kind of in their own standard custom format. And so for that, you'd have to manually parse your data set. So you do like a snapshot download from Hugging Face to your local directory. And then, you'll end up with a data set that is essentially Parquet files. That Parquet file will have the features, and then usually that media is some type of base64 encoding. Then you have to convert that base64 encoded thing into an actual file on disk. Then iterate through your Hugging Face data set, grab the features, add them to the appropriate sample fields on your 51 data set, point to the file path that you've just used, that you just converted with that Parquet, and then just, turns into a 51 data set. We have, for those of you who are big on, LLM workflows and using scales and MCP, I highly recommend checking out this repo. And in this repo, there's some commands here for importing data sets. So it's a skill for how to import a data set. So if you see a data set on Hugging Face and you want to try to get into 51 itself, then just go ahead and look at this skill, and it'll work for you. It's pretty good. All right. So you can imagine how tiring it would be just to like look through these data sets, open each one of these captions, and look at, for example, try to look through each one of these videos, understand what's in there, and trying to get a sense of how similar are some videos and dissimilar. Like it's tedious, right? Like there should be an easier way to do that, and there is. And in this case, we're going to use embeddings. So there's a couple of really interesting models that came out. This one came out last month, January 2026, Qwen3-VL embeddings. So this is a model that you can use to compute video embeddings and then do natural language search over your data set. And I'll show you how to do that in a second. But as I mentioned, 51 is hackable, extensible. Yes, we do have a model zoo, but that model zoo might not have the model that you are interested in working with. Well, you can implement that model as what's called like a remote source zoo model. And so a huge part of my job here is to integrate these new models. And so I'll drop a link to that, and just to show it here on GitHub. So this is the Qwen3-VL embeddings model. And you can see it's just implementing this zoo.py. If you're interested in implementing a model, like hit us up on Discord. Maybe Burhan, you can give us a link to the Discord channel so people can join in. But the point being here is just this: like it just is easy for you to get up and running with a model in 51. So we just register the zoo model source, load the model, set a parameter on this model. In this case, let's set the max length, and then just dataset.compute embeddings, and that's it. And so it'll iterate through the samples in your data set, grab the videos, compute embeddings, add those embeddings back as a field on the data set. And once you have those embeddings, you can actually do a visualization of those embeddings. So in this case, we're going to do a UMAP visualization. And once we have a UMAP visualization, as you see in the app, we can open the embeddings panel and kind of see the manifold of the data manifold that we have with this little subset of data. We could build a similarity index here. And as I'll show you in the app, the similarity index will allow us to do natural language search. And this same model, the same Qwen3-VL model, we could use for zero-shot classification, right? So this data set itself from FAIR, like it didn't have classes like to tell us like, what class or what category this video falls into. They mentioned that they use classes from like WikiHow, but they don't have those. And so what I did here was just use that same embedding model and try to do some zero-shot classification, right? And so now we could see this in action here. First thing I want to show you is the embeddings panel, right? So open up the embeddings panel here, and then also just showing you that the same pattern is used for Molmo. So I'll go back to the app in a second here, but for Molmo2, this model itself is a vision language model, and I kind of hacked the model to be able to produce embeddings for us. So the model itself isn't made for generating embeddings, but yeah, I did some hackery with it and implemented it, made it easy for you to compute embeddings with this model. And then the pattern you'll see here is the same: compute visualization, compute similarity, and we're actually not limited to just text. We could actually, just videos, just images. We can compute videos using text as well. So just kind of real quick, before I jump into that, sometimes I get excited and get ahead of myself. Before I get into the text embeddings, just to tell you what we've done here. If there's questions, let me know. So up to this point, I've used two open models, Qwen3-VL embeddings, and then also Molmo2. We've taken every one of the videos, computed a embedding for that video, so kind of a vector representation of that video, and then we did some dimensionality reduction using UMAP so that we could easily visualize those in the app. And now when we have this, we expect some kind of structure in the data set that maybe shows us videos that are similar to one another within that embedding space. So that is what we're looking at when we have the embeddings panel here, right? And what I'm going to do is actually I'm going to color by the class that we predicted using, in this case, Qwen3-VL. And so you can see here, we see some structure kind of in the data set. Like, for example, there's like an island of videos down here. If we were to highlight this island of videos, it would filter down to the app. And, we can see that the if we do a GPT summary brief, technician, adds polyprothane, man in blue t-shirt, so on and so forth. Like there's some type of work with looks like cars happening in this particular cluster of videos. So now what I want to do is highlight a few samples here, right? And pay attention to where these are in the Qwen3-VL embedding space, right? If I now look at the Molmo embedding space, I see that the embeddings generated by Molmo have like a different structure to them. And in some ways, it almost looks like there's a bit more kind of separation, right? And we can see that where these three videos are, like, let me just filter, let me just make it a little bit more meaningful. Going back to Qwen here, let's click on this video. Let's show the 5 most similar samples. And then if we were to highlight every one of these, if we click here, we see, okay, that similar video is there, that similar video is there. It's kind of all in a neighborhood. So remember, this is in 2 dimensions. If we're looking at it in like 3 dimensions, in that third dimension, they might look a little bit more tighter. And what these yellow dots represent here, these are just that video in the embedding space, right? So I'm just highlighting this video. That's where it is in that embedding space. So it's just saying, okay, this video is that particular point, right? And what I did was I sorted based on the Qwen embeddings. I sorted to get the, according to that model, the 5 most similar videos to this video, right? Now, if I switch this to the Molmo, we see, okay, they still look relatively close to each other in the Molmo space as well. So I encourage you, once you get your hands onto this data set, what you want to do is just play around with this, with these, you know, uh, with this, like I can get lost looking at embeddings for hours. And so all this is, of course, it's done in the FiftyOne app. It's just a panel in FiftyOne. You just hit, once you've done this process of computing the embeddings, computing the visualization, and then building a similarity index, then you could do the sort by similarity and visualization of embeddings. So an interesting thing is we can actually perform natural language search. So Molmo2 is not a model that's tailored for natural language search over a corpus of data, but Qwen3-VL embeddings is kind of built purpose for that. So what I could do is maybe say, find me the 10 most videos of making a salad, right? And perform natural language search over the data set. So these are all like I typed in making a salad, right? And we can see here all these videos more or less look like they are involve making a salad. This one might involve making a salad, but it looks like they eventually somebody is making a salad in this video, right? So this is just doing natural language search over our video data set. So just to show that again, we're only able to do this with the Qwen3-VL embeddings model for this demo because that's the model that is tailored for this particular task. Click on sort by similarity, click on this gear button. Let's just do 10 most videos. And maybe I want to do a video about, I don't know, man, give me a topic. Fashion for techies. I don't know, like just fashion for techies, right? And we can see what shows up. All right, well, that's an interesting video for fashion for techies. Maybe you want to see a video that's, do we have any videos that are maybe all about fixing Honda vehicles, right? Yeah, and so you can see here, like videos that come up, that's clearly a Honda. This intro scene is black, but yes, it's a Honda. And yeah, we're able to do this really interesting natural language search over the video. So yeah, pretty powerful, pretty cool stuff. I mean, I think it's awesome. I think it's so dope that we're come this far with open models. Like having a model like Qwen3-VL is something I've been wanting for a very long time. And I should power through the rest of this because I'm noticing time. We're not limited to just computing embeddings and visualizing embeddings using videos. In this case, what I've done is I've used the Gina embeddings v5 to compute embeddings based on the transcript. And so that's what's happening here. All I'm doing is I'm extracting using the values method of the dataset, extracting the transcript, passing it to the model, and then adding it back as a field on my dataset, computing visualization and computing similarity. So here, now what I could do, going back to embeddings, and then I could visualize the transcripts, embeddings of the transcripts, right? And if we color by, for example, the predicted class, we could see that, we get a little bit better clustering just based on the transcript than we do based on the video itself. And just this is a very, very small model that we're using. I think this is less than 200 million parameters, whereas the embeddings that we got for Qwen and Molmo are like, I think from 2 and 4 billion parameter models. But like we could do something like this. We could highlight these videos, right? And we have keyboard shortcuts in FiftyOne, but my keyboard shortcuts are pinned to using cursor, so they won't work. But we can say, okay, all of these videos here, how similar would they be in Qwen embedding space? And it says, okay, they are actually pretty close in Qwen embedding space. How close are they in Molmo embedding space? Well, they look a little bit further in Molmo embedding space. But we see that, more or less there seems to be some level of agreement between, semantic agreement between the actual embedding spaces that we get. You saw that we did some zero-shot classification using the Qwen3-VL embeddings model. And so what I'm going to do now is do the same kind of thing, but using GINA embeddings v5 text classification using the transcripts. So just grabbing all the titles, grabbing all the descriptions, concatenating them, so title plus description, creating using that model to create embeddings for this title description that we just created, creating embeddings for each one of these classes, and then using cosine similarity, right? And then once we have cosine similarity, I'm just going to add this back to 51 as a classification field, right? So once it's added back as a classification field, we're able to view it in the app like this. And let's see here, there was another one that I created, predicted class, right? So as I mentioned before, we don't have ground truth classification for the video that came on the data set itself. So we could just assume, for example, that the ground truth is going to be the Qwen models classification. And then we could run like a classification evaluation for those classifications right here in 51 using just a couple lines of code. We do this, and then we can open up the app here, look at model evaluation. We have the evaluation here, and we could see, okay, the average confidence for the GINA predicted class. We can see the metric performance. We can see class-wise performance. And then we also got a confusion matrix that we can interact with here. So we can interact with the confusion matrix, and it'll filter down in the app as well. So all super interactive and really a visual way for you to see how well a model performs. We also have scenario analysis, so you can create scenarios here. So not to go too much into this because we haven't talked about these yet, but we could do scenario analysis based on different fields on our data set as well. So yeah, just touching on that. So okay, visualizing the embeddings and doing all that, that's interesting enough, but we want to be able to get more insight from the embeddings. And what we could do is actually compute uniqueness values and also representativeness values. So I'll let you read what uniqueness and representativeness mean here in more detail. But essentially, uniqueness just measures how different or dissimilar a sample is from the neighbors in its embedding space, whereas representativeness just shows how typical or central a sample is relative to the rest of the data set in the embedding space. So here, what I've done is I've computed uniqueness and representativeness for the Qwen embeddings, and I could leave it up to you to create the uniqueness and representative values for the other embedding fields. But just to show you what it looks like here, like we can go to the embeddings, and you can see here we have now a field here called there's a lot of fields. One of them is uniqueness down here somewhere. Anyways, I'll just pull this up and then color by Qwen uniqueness, right? And we could see kind of, the distribution of those uniqueness scores and also representativeness scores as well. You can also, of course, create the dashboard, just a quick histogram using this uniqueness field, right? And so here you can then filter down, okay, like what are the most unique videos like in my data set? And you could. Oh, well, I guess the dashboard is interactive. So let me open the dashboard. You can go to dashboard, add a plot. We'll do a numerical histogram. We'll do Qwen uniqueness. Just create the plot, and then we can interact like so. And so it filters down, okay, what are the most kind of unique videos from what we have. So yeah, that's what we're doing there. Going back to this notebook here, questions that are coming in. How do we select the right embedding space? I don't think there's any such thing as the right embedding space. I think you use one that will fit your compute budget and your resources for sure, and one that's tailored for your task, right? So that's kind of the general rule of thumb. That's how I would approach that. So real quick, just showing you something else. This is a kind of comfy UI type of templated workflow that I've built. It's in the description of the README, but we could do everything that we just did right here, like this compute uniqueness, compute representativeness. We could actually do something similar using this right here. So for example, let's curate by uniqueness. I'll remove this node because I already have embeddings, and I could do a uniqueness view. What I'm going to do is compute the uniqueness score from Molmo, and then I'm going to sort to get the most unique samples based on Molmo uniqueness, and then it'll filter that down into the sample view here for me. And then this will be the app will filter that down. Well, it's not filtering, it's actually, well, it is filtering to the 100. Well, you could change that, right? That's why there's 100 here. But what we see in the sample grid now is the 100 most unique videos based on the Molmo uniqueness score. So of course, you could probably change the name of the uniqueness field as well. And likewise, you could do the same thing for representativeness. Just, remove that, pick the right embeddings, and then run the workflow. Very much experimental and very, in work in progress, but I was inspired by Comfy UI. And so that's kind of where this idea came from. So questions, sometimes 51 is very slow with large. Yeah, how to improve it? This is the local version of 51, so a lot of it is this is a local version working in an IDE browser, which is going to be, I think, slow. You probably have better snappiness in your own browser, but then also we have an enterprise version. So if you're working in an enterprise setting, you could look into that, and that'll be a lot quicker as well. All right, so just moving along. Thank you guys for sticking with me. I know we're going through a lot. What I want to show something interesting here is kind of this cross lens, what I call a cross lens moment. So what I've done here is I'm going to only consider the root labels for GPT summary brief. And what I'm going to do is I'm going to look for, I'm going to sort by similarity for the Qwen similarity, find the most unique neighbors based on that, and then again, based on Molmo, based on text, right, that are similar to one particular video. And just to kind of get a sense of how different or similar those embeddings, representations are to, what this reference video is. So that's just what this is doing here, right? So I'm saying, okay, this is my reference video. This is the summary of that reference video based on Qwen embeddings. Here's what the nearest neighbors say the video are. Likewise for Molmo and text embeddings as well, right? So kind of moving along. The next thing I'm doing here is I'm showing you how to essentially use Qwen3-VL, like the actual vision language model now, on this data set. And what I've done here is just register the Zoom model source, instantiated the model, and then put the operation in description mode. Here's the prompt that we get in description mode, and then I apply it on my data set. So when we look at any particular sample, I could open this caption viewer, and I can look at, I think I called it Qwen, what did I call it? Qwen discovery. Qwen description. So there's Qwen descriptions, there's a comprehensive description, and then we'll also get a summary description as well. And so kind of a different lens on what the video is. And of course, you could follow the same patterns that we just did to then compute the text embeddings for this and visualize it and kind of get a good understanding of what's in the data set, right? So everything that we are doing here, every field that we're adding, all these embeddings and all this is just for us to better understand the data set. Another thing that we could do is use the Qwen model in comprehensive mode. And when we do it in comprehensive mode, we get a lot of additional fields for our data set. So here we have the comprehensive, it's going to be the summary, the objects, events, text context, content, scene info, activities. Like this is what I'm prompting the model to produce for each video at certain timestamps. So everything will be, all the fields generated will be preceded with Qwen comp. So if I go Qwen comp, we see the summary here, but then we can also scroll here and see Qwen comp summary. I think that was the only one that's generated. Okay, Qwen comp summary. And we have, let me clear these fields. We have Qwen comp events, objects, text content, scene information, like all this really rich information. Hard for me to see in the side panel here because I have so much of it. Well, it was actually all up here. So we have the events, objects, text content, scene info, right? A lot of rich data that we did not get from the dataset authors themselves. We can create that for our dataset. So for example, like, this prompt here, scene info, we get the setting, which is a one-word description, time of day, location type, right? So we could say scene info, location type, and let's say I'm only interested in locations that are taking place, for example, at the baseball field, right? And I can get that video. And you could hide these labels if you want, clear them out. Or if I'm interested in the time of day, I could filter that down here, right? Like, do I have videos that are in an overcast setting? Okay, well, is this actually overcast? Well, it looks like it's an overcast, and you can see that actually is overcast based on kind of that guy's background there. So just adding a lot of interesting metadata that we could then go create a dashboard, and then we could do a categorical histogram on that dashboard. We can go to Qwen comp. We can look at maybe scene info labels, sort it by frequency, get an idea of, okay, what types of locations are in my data set, and kind of rinse and repeat. And I'll leave this as an exercise for you. So you can create another categorical histogram. For Qwen, we just did, I think, time of day, I think, or primary activities, and then sort by frequency and create a plot and Okay, right? We can see, yeah, there's a lot of cooking videos that, of course, happen in the kitchen, and we can filter a little bit further here and see, okay, like what are all these, you know, car maintenance videos, and then it'll dynamically filter the other uh, plots in the dashboard as well, and we can start looking through here and see, okay, these are all the car videos that we have, right? So you can see now that we're able to really better understand our data set by enriching it with more fields that the dataset authors didn't get. So we're able to do this type of workflow and just get really comfortable and familiar with our data set. So the next thing I want to do is in the paper itself, there's a prompt on page like 17, I think, of the paper. And I'm going to prompt both Qwen3-VL and Molmo2 to, with the prompt from the paper. That's what's happening here. Running running this prompt with those models on the data set. This gives us a raw string, which will look something like this, for example. We could pull this up, open the caption viewer to the side. I prompt the model, and I get a string that looks like this, essentially, right? Because this is what I prompted the model to output. I did that with Qwen and with Molmo as well, somewhere here, Molmo, right? And this is just a string, and I'm converting these strings now to 51 kind of sample level fields. So for example, you can see here, if we go to, it'll be like Molmo action actor, right? So you see here, a man with dark hair, blah, blah, blah. And you can see here, that's, the string where it's coming from. So it becomes sample level fields. So that's what this code is doing here. It's taking the string object that the model gave us, loading it as JSON, extracting the fields that we need, and putting it back onto the data set as sample level fields. Likewise, what I'm doing is I'm taking the GPT root level nodes, root level fields for all of these, and then adding these as top level sample fields. And the reason I want to do this is because now I could measure alignment, right? So I'm using this plugin for text evaluation metrics. And so the first thing I'm going to do is measure agreement using this metric of normalized Levenshtein similarity. So you can read about what that does here. And I'm comparing the Qwen-VL summary brief to GPT summary root brief, and I'm storing it in this sample level field. And likewise, I'm doing something similar here, but instead I'm using a sentence transformer model to do semantic similarity using cosine similarity. And it's the same type of workflow here. I should probably run this. And then what I'm going to do is tag samples. These are arbitrary. You could adjust these as needed. And then I could tag samples that, okay, where do all the models disagree? Where does Qwen only agree? We see the Molmo doesn't really have much agreement. And this is, again, just based on the detailed summary field. Molmo doesn't have much agreement at all with the ground truth, quote unquote, ground truth. But if we want to get more kind of in depth, what we could do is, create another dashboard. And what I could do is create a scatter plot, and the Y source, I can have that be the, let's just focus on Qwen semantic. So semantic, let's do semantic Qwen action brief. And then this will be semantic Molmo action brief, create a scatter plot. We'll open up to the side here, right? And then we can filter down on the scatter plot to see, okay, like which, we can see how this spread looks like, but like what are these samples here, for example, that are mostly in agreement. It'll filter down what we're working with here. And we could, spot those videos, right? And better kind of explore and understand the distribution of semantic scores, right? So going through a lot here. I know there's a ton that we covered, ton that we went through. Everything is right here in this notebook. You could just read this on your own time, and hopefully this will be illuminating. I encourage you to try this out. But essentially, what we've done is this, right? Everything in this notebook was just to help us better understand the composition of our what was it, 26 hours of data without having to watch 26 hours of data. And so that's what we're doing here. That's the whole purpose of the workflows we're undertaking here is how do we better understand what's in our data set? How can we do that using open tools? So what we did was 3 different views of the same data. We did Qwen3 embeddings, Molmo embeddings, transcript embeddings. We came up with independent second opinions on the annotations, at least for the root level, using Qwen3 and Molmo. We did some similarity using some text evaluation plugins. Just to show how this plugin works, like I showed you how to do it in the SDK, but you can also just do it in the app as well. So that's something that that plugin allows you to do. And this gives us an idea of which one of these models tends to agree most with this ground truth that we get from a larger model, right? And if we're able to assess this on a subset of our data, it helps us choose the right model to use on the entire data set, right? So this is kind of like the end goal of doing all this, right? Exploring our data set, understanding what's in it, using some measures of similarity and agreement to then figure out, okay, like if I was to try to recaption this data in a different way, but wanted to do it within the compute constraints that I have, selecting from a few different models, like how would I go about doing that? And so that's what this entire workflow and workshop covered. So a lot of questions came in through chat. I think I hit them all. I appreciate you guys staying over. And if there are questions, let me know in the chat. I don't think there's anything that I missed in the chat. Question here, how do we select the right embedding space, the way to quantify embedding space? Yeah, again, I think I answered that. It's just, it depends. I mean, you can quantify embedding performance. I don't know, because the embedding spaces are different, right? So two embedding models will fundamentally represent different embedding spaces. So trying to do some type of evaluation across embedding spaces might not work. But I would say you want to maybe choose an embedding model that gives you the most cleanest separability. Can we add a new model to do embedding and integrate into FiftyOne? Yes, absolutely, you can. And you can look at the patterns, for example, here. This will show you kind of the general pattern for how this will work, so that you can use it quickly with FiftyOne, using the apply model and getting all the benefits of speed up and things like that. But if you need help, hit me up on Discord, and we'll help you implement an embedding model. Like we've got, like for example, like I showed you Qwen3-VL embeddings, but if you go to my GitHub repo, you'll see that I've got embedding models for MedSiglip, of course, Siglip2. There's some other ones that I did specifically for like document retrieval, a bunch of them. Yeah, Gina embeddings, V4, that's a good one. Nomic, BiModernVert, Cole ModernVert. These are all like document retrieval models. So just kind of showing you that there's different ways, and you can just look at the patterns that I've previously used.